To summarize from all the features that we've talked about so far, the sign of the first derivative tells us the interval where the original function is increasing or decreasing. The first derivative also tells us the stationary points, and this is when we have zeros on our first derivatives. That's when the first derivative is equal to 0. So then that would be zeros of the first derivative indicate stationary points. Those are your maxes and those are your mins. Potentially stationary inflection. It just kind of depends on the shape. The sign of the second derivative also tells us the shape of our original function. Shape being concave up and concave down. Okay, the zeros of the second derivative, or where the second derivative is equal to 0, indicates points of inflection, also provided that the second derivative is changing signs at that respective point. You use all those features and a little bit of intuition to connect all the graphs of the original, the first derivative, and the second derivative together. So that's what we're going to be concentrating on today. Lots of graphing. Okay? So let's do that. Everyone, do your best to copy down this diagram as we are going to graph the first derivative and the second derivative of this function. So when we look at this particular graph, and in the process, we're going to graph the first derivative and the second derivative, those points A, B, and C, they indicate very important points that we do need to be aware of, okay? A lot of times on the IB exam, these points won't be highlighted as distinctly. You'll just need to be able to see them within the graph. This is the first one that we do, so of course they are labeled, so in that way you can kind of keep an eye out for them. When you look at point A, what does point A look like to you all? Like in context of the original function. What does A represent?
Y-intercept.
It does represent a y-intercept. That is very true. What other feature of the original function is point A besides a y-intercept?
The global minimum.
It is an absolute or a global minimum, okay? So yes, A is a minimum. And remember, minimums exist when the first derivative is equal to 0. So if we have a minimum, that means that on the derivative, we have an x-intercept at that same x value. What about B? When you look at B, what does B look like? Like I said, it's not the most defined graph we have, but it has a few features in it that we, like I said, we need to be aware of. What does B look like?
Stationary inflection point.
Can you elaborate a little bit more on that? Like, are you sure it's a stationary inflection point?
Oh, critical point, is that the other one, the other term?
So are you trying to associate it with the first derivative or the second derivative?
First derivative.
Okay. So if it's a stationary inflection point, that means that it had to kind of level out and then continue to increase before and after that particular point. And in actuality, that's not necessarily B, that's more so C. C is right over here. C would be an example of a stationary inflection point because the graph levels out. It was coming from an increasing motion, levels out, and continues to increase. And remember, at stationary inflection points, that's where the first derivative is equal to 0. But at C, and we'll go back to B and address that as well, when you look at point C, before C and after C, how would you describe its curvature?
Concave down and concave up.
So because it had changed in concavity, that means that the second derivative is also equal to 0. Okay, so C is a stationary inflection point, but that also means that on the second derivative as well, because it's going from concave down to concave up, it's going to have an effect on the graph of the second derivative also. Point B is actually just an inflection point. It changes from being concave down to concave up very, very minimally, but it does happen. And again, that's where the second derivative is equal to 0. Highlighting these things to help us in graphing the first derivative and the second derivative. So now that we've identified each of those points, now let's graph the first derivative and second derivative. Gonna graph them separately to make sure that everybody's understanding. Now, from negative infinity to point A, can we agree that the function is decreasing? So if it's decreasing from negative infinity to point A, then that means that the first derivative is less than 0. And to be less than 0, that means you need to be below the x-axis. So from negative infinity to point A, we are below the x-axis because the original function was decreasing. Now from A to B, the function is increasing. And if it's increasing, that means that the first derivative is positive, which means that the graph of the first derivative needs to be above the x-axis. However, once we get to B, which was an inflection point on the original graph, there's actually an extrema on your derivative at point B. From B to C, it's still increasing, just not increasing as much. Okay, so that means that it's still above the x-axis. But remember, at C, the first derivative was equal to 0. So it's going to have to touch the x-axis at C. So the graph of the derivative, first derivative, is going to be still above the x-axis, but it needs to be coming to the x-axis to touch at C, because again, C was a stationary inflection, and again, it leveled out on the original graph, so that meant the first derivative was equal to 0. After C until infinity, the function is increasing, which means that the first derivative is still positive. So it doesn't go below the x-axis because basically from a until infinity, the function is still continuing to increase. So I need to be above the x-axis until positive infinity. And that would be the graph of your first derivative. So where the original function is decreasing, the first derivative is, let me start over. Where the original function is decreasing, the first derivative is negative, which means it's going to be below your x-axis. Where the original function's increasing, your first derivative is going to be above the x-axis. Whenever your first derivative is equal to 0, you're going to have x-intercepts on your first derivative. And if there are any inflection points on your original, there's going to be some extrema on your first derivative. Let's look at our second derivative. Remember, second derivative talks about the curvature of our original function, okay? And as we pulled out and highlighted a few things, we were able to determine that B was an inflection point, which means the second derivative is equal to 0, and the same thing with C. So that means where the x value of B, there's going to be an x-intercept, and the x value of C, there's going to be an x-intercept, because at those points on the original function, that's where that's where the second derivative was equal to 0. So similarly to what we were doing before, we're talking about the second derivative now. From negative infinity to point B, the graph is concave up. Where the graph is concave up on your original, that means your second derivative is positive. So then that means that from negative infinity to point B, we should be above our x-axis. From B to C, we're concave down. If we're concave down, that means the second derivative is less than 0. So then that means our graph of our second derivative should be below the x-axis. Remember, at point C, the second derivative is equal to 0, so that means it has to come back up to touch that x-axis. From C until infinity, the graph is concave up, so then that means the second derivative is positive, so then it should be above the x-axis. So this would be the graph of your second derivative. So let's practice. We are going to sketch the graph of the first derivative and the second derivative using this function that we see here, okay? So let's pull out some critical points here on our original function. Since this is a quadratic and it's pointing up, or it looks like a quadratic and it's pointing up, this point right here represents, I'm going to go ahead and label it A, represents a what?
Minimum.
Global minima.
It's a minimum, it's global minimum, which means that if there's a minimum, that means that our first derivative is what?
It's 0 there.
It's 0 there. It equals 0 there, which means that on our first derivative, if there's a extreme of any kind, that means we're going to have an x-intercept on our first derivative. Now our function, if I go from left to right, from negative infinity to positive infinity, it is decreasing from negative infinity until that point A, which I drew in. And then from point A until infinity, it's increasing. So if it's decreasing from negative infinity to that point A, that means the first derivative should be what?
Below the x-axis.
Negative.
It should be negative. It should be below the x-axis. So that means that when I draw it, it needs to be down here, below the x-axis. But then after that point, the original function was increasing, so that means it should be what on the first derivative?
Above the x-axis.
So then it should be positive above the x-axis. And that is our first derivative. Now, when we look at our original function, do you see any inflection points? Where it changes from being concave up to concave down or vice versa?
No.
No.
Concavity is the same.
If the concavity is the same from negative infinity to positive infinity, it's concave what?
Up.
It's concave up. So if it's concave up from negative infinity to positive infinity, that means that the second derivative needs to be what?
Above the x-axis.
It needs to be above the x-axis because it's positive. So the only way that I can represent the second derivative so that it will always be above the x-axis from negative infinity to positive infinity is my second derivative needs to be a horizontal line that intersects the y-axis above or in the positive area. It cannot have any type of slope to it, because if it has some type of slope to it, that means that it would be intersecting the x-axis at some point, indicating that there is an inflection point on my original function, which there isn't. And there's the graph of the first derivative and the second derivative. Something else that could help, and it definitely helps for the types of functions that kind of look like something we know. The original function, and I said quadratic by accident, but I mean, that's what it looks like, right? It looks like a U. If my original function is x squared, which I know it's not because the origin is not at 0, 0, but just follow me here. What's the derivative of x squared?
2x.
And 2x looks like a line, right? With a positive slope. That's what we drew. We drew a line with a positive slope. What's the derivative of the derivative? What's going to be the second derivative?
2.
2. That's a constant. A constant is a horizontal line. And on top of that, it's positive, so that's why it's above the x-axis. Y'all follow me here? Like if you kind of keep that in your mind, then drawing the first derivative and drawing the second derivative can help you. Because if the original function looks like a quadratic, that means that the first derivative has to be a line. You just have to use the original function to determine if it's a line going up or a line going down. And then from there, you can derive your second derivative. Okay, same thing. let's sketch the first derivative and the second derivative based off of this function. Okay, based off of this function. Now, when I look at f of x, okay, let's pull out some key features of the original function. What do you see?
Critical points at plus or minus 2.
Ooh, now careful, these are -2 and +2. Those are x-intercepts on the original function. Those actually don't have any effect on our first derivative or our second derivative.
No.
Go ahead. Thought I heard something.
It changes concavity.
It does. It does change concavity. Where?
It starts out like on the negative x, because I'm assuming it goes through the origin. On the negative x side, it's concave down, and on the positive x
Okay.
axis, it's concave.
Okay, you're a little glitchy, but I think I was following you a little bit. You were saying on the left side of the y-axis is concave down, and on the right side is concave up. And so you said at the origin, so I'm assuming you said that that point at the origin is an inflection point. I'm thinking you said that, but you were kind of glitchy.
I didn't say anything about an inflection point, but that's cool too.
Okay, well, I figured if you were talking about concavity, remember where concavity changes from being concave up to concave down, that is that point where they change. Remember where my fingers are meeting? That is going to be an inflection point. So it's good that you recognize that, okay? It's good that you did recognize that, but got to make sure that you indicate that inflection point, because then that means that on our second derivative, that's where it equals 0 on our second derivative. What else do you guys see? On your original function?
Is there like a local maximum and a local minimum?
Yes, there's a local maximum and there's a local minimum. And remember, local maximums and local minimums mean, are they associated with the first derivative or the second derivative?
First.
The first. That's where the first derivative is equal to 0. That means there's x-intercepts at those respective points, at those extrema, okay? And remember that if you have an inflection point on your original graph, you also have an extrema on your derivative. Okay? So from -infinity to point A, the function's increasing. That means you need to be above the x-axis until that point. From A to C, we're decreasing. That means we need to be below the x-axis. And more specifically, there is going to be an extrema on our first derivative at that point B. So I'm going to make that turn at B to go back up to meet at my x-axis. And then from C until infinity, it's increasing, so that means it's going to be above the x-axis. And that is our graph of our first derivative.
Would that be like the first derivative? Would that be like a quadratic, or do you not know for sure?
It would, well, we can use that to help guide us, because since our original was a cubic, when we take the derivative of a cubic, that gives us a quadratic. So we can use that to help us when we get to graphing. Now, of course, that won't really help us if we're given anything, you know, that's kind of outside of like our normal polynomial functions. Then we're going to really have to use, you know, the fact that, you know, if we have an extrema, or if we have a max or a min, that means we have an x-intercept on our first derivative, and so on and so forth. But I'm trying to, you know, hopefully you can make the connections with the more simpler graphs, so in that way, when you get to the more complicated graphs, you'll be able to use those, you know, these key features. So on our second derivative, remember, wherever there's an inflection point, there's an x-intercept on our second derivative. So at 0, 0, we're going to have a x-intercept, and it is concave down from negative infinity to that point B. So that means we need to be below the x-axis. And then since it's concave up from B until infinity, we need to be above the x-axis. So then this will be the graph of our second derivative.
Explain the second derivative line again.
So remember, second derivative talks about concavity, okay? So if we're able to see that it is concave down from negative infinity until 0, then that means it's going to be negative on our second derivative, or in other words, below the x-axis. But from 0 until infinity, it's concave up, then that means it's going to be positive on my second derivative, or above the x-axis. And the thing is we want to draw it as a straight line versus a curve, because if it was a curve, then that would indicate that it could potentially hit the x-axis somewhere else, and then that would indicate other things on your original function that aren't there. Try this one on your own. Try this one on your own. So on your original function, hopefully you identified that there were two extrema. One here at that point, and then another one at 3. And remember, anytime that you have an extrema, whether it's a maximum or a minimum, that means that on your first derivative, you have an x-intercept, because that's where the first derivative is equal to 0. Now, because the graph is increasing from negative infinity to positive infinity, that means that you are going to be above the x-axis. That means you're going to be above the x-axis from negative infinity to point A. I think I might say negative infinity to positive infinity, that was my mistake. You're increasing from negative infinity to A, so that means you need to be above the x-axis from negative infinity to A. Now from A to B, you're decreasing. So that means you need to be below the x-axis. But in order for you to basically go below the x-axis and then come back to the x-axis, you have to have an extrema on your first derivative. In order to have an extrema on your first derivative, that means you probably need to have an inflection point somewhere in between those extrema. So we have an inflection point halfway between that max and that min. And because we have that inflection point, that means we're going to have an extrema on our first derivative at that respective point. we are decreasing from A to B. So that means we need to be below the x-axis. And then we're increasing from B into infinity. So that means we need to be above the x-axis. And this is the graph of our first derivative.
Could you repeat why we have an inflection point of C between A and B?
Okay, so in order for a curve to change its curvature from being concave down to concave up, there had to have been a point where it made that change. That point where it makes that change, that is where the second derivative is equal to 0, because we're changing from being concave down to concave up. So we're going from positive to negative on that second derivative. And yeah, and also that is that point. There's that point. And anytime we have an inflection point, we have an extrema on our first derivative. So then on our second derivative, again, talking about its curvature, we're concave down, concave down from negative infinity to C. Then we're concave up from C to infinity. So again, wherever there's a point of inflection, we have an x-intercept. Concave down means we are below the x-axis. And then concave up means we are above the x-axis. So then this would be our second derivative. You want to definitely make sure that you try to hit some of those crucial points of extrema, inflection points, to highlight when you are graphing the first and the second derivative. So one last thing that we're going to try to do is we're going to try to go the other way. Now, I might regret doing this, but we are talking about the graphs and the features of the graph. And so we're going to try to go from our first derivative to our original function. This is doable. We can do this, okay? We just have to remember, what does the first derivative mean? The first derivative means that that's where the function is increasing. That's where the function is decreasing. That's also where the original function has maxes and minimums. And it's also where, like we have to use all those things. So here we are given the derivative. This black curve represents the derivative. And then remember, when it comes down to the derivative, not the second derivative, sorry, where the first derivative is equal to 0, that means we have an extrema. That means we either have a max or a min. If the first derivative is greater than 0, that means we are increasing on our original function. If the first derivative is less than 0, that means we are decreasing. Okay? Anytime we have any extrema on our first derivative, that means that we have some type of inflection point on the original. Okay? So all these things we need to keep in mind. We need to keep in mind. So as we can see on the first derivative, we are above the x-axis from negative infinity to negative 3. If we're above the x-axis, that means we're positive. So then that means from negative infinity to negative 3, the function is increasing. Does everybody see that? Make the connection. From negative 3 to 1, we are below the x-axis. We are decreasing. okay? And actually, we're decreasing the entire rest of the function, okay? We're actually decreasing the entire rest of the function, all right? From -3 to infinity. Because again, the first derivative is below the x-axis. The first derivative is negative. So then that means we're decreasing, okay? But we do need to highlight that point at 1, because at 1, let me change colors again. The first derivative was equal to 0. But the thing is, it didn't go from being negative to positive or positive negative like it did at -3. At -3, it went from being positive to negative, which means that we're going to have a maximum on our original function, because that's what it means. Positive to negative means that there's going to be a maximum. But at 1, the first derivative was equal to 0, but we didn't change from being positive to negative or negative to positive. So what do you think is happening on the original function at 1?
Is it stationary?
Are you saying stationary?
Yes, ma'am.
Okay, yes, there is a stationary point at 1. What type of stationary point? Because stationary points could be maximum mins, but they can also be inflection. Is this a stationary maximum min point, or is this a stationary inflection?
Is it a stationary inflection? Because it looks like it changes. No, wait, that's for the second derivative, but it looks like it changes concavity.
Okay. Well, it is a stationary inflection point, but remember, this is representative of the this is the curve that I drew over is representative of the first derivative. Okay. Because we went from negative to negative at 1. Remember, if we go negative to negative, that means we have a stationary inflection. Okay. Or if we go positive to positive, that means we have a stationary inflection. Okay. So let's see, is there anything else? Is there anything else? Remember, if we have extrema on our first derivative, there's an inflection point on our original function. So one last thing that we can pull out is that this extrema right here, at this random point, maybe like around -1.5 or -2, right here, we are also going to have an inflection point, but it's not going to be a stationary inflection point because it doesn't touch the x-axis. This one's going to be a non-stationary inflection point, or just a true inflection point. On our original function. So we're going to graph this, and I'm going to use this like tan color here. So I need to be increasing from -infinity to -3, and I need to have a maximum at -3, okay? I am going to draw my maximum up here. Will it really matter? No, not really. You could draw below the x-axis, but there's a lot of stuff going on in this picture. So I need to be increasing from -infinity to -3. Then I need to be decreasing the rest of the way. Now at this one point here, I do need to change my curvature. So at this point, I'm going to be decreasing. Oh, that's ugly. Trying to smooth the curves here. I also need to have another inflection point at 1, but I still need to continue to be decreasing along the way. This point could be above the x-axis, it could be below. It really doesn't matter as long as you continue to do what it is that the first derivative is telling you to do. So I need to be decreasing after -3. I need to change concavity between this random point and +1. And then I need to change concavity again afterwards, but still continue to be decreasing. And that would be the function, the original function. So it doesn't matter whether you're above or below the x-axis when you're graphing the original function, because unless they give you specific points on your original function, there's no way to know exactly where this function is going to like intersect the x-axis, for example, or intersect the y-axis, okay? All we know based off of the first derivative is that there's a maximum at -3, there's an inflection point at this 1x value, and then there's another inflection point at 1. But we need to be increasing until -3 and decreasing the rest of the way. So as long as you're doing that, it doesn't matter whether your maximum occurs above the x-axis, below, or if you cross the x-axis at some other random point. So to finish up this last problem, I wanted to give you guys, again, we are practicing sketching the original function from the first derivative. And so we have this graph here. And so we want to use the different features on this function to graph our original function. So remember, wherever there are x-intercepts on your first derivative, that means there's potential extrema or stationary inflection points on your original graph. So as we can see that at x equals -2, we are, or excuse me, there's something happening at x equals -2, and there's something happening at x equals 4 because we have x-intercepts. That's where the first derivative is equal to 0. From -infinity to -2, our graph is less than 0, okay? Which means that the first derivative is negative. But then from -2 to +4, the first derivative is greater than 0, which means that it's positive. So that means at -2, if we go from negative to positive, that means that we're going to have a minimum on our original function. From 4 to infinity, the first derivative is less than 0. That means that it's negative. So if we go from positive to negative at x equals 4, that means we're going to have a maximum on our original function, okay? So we're going to have a maximum on our original function. We're going to have a minimum on our original function at these two respective x values. And remember what I said earlier, is that if you have a maximum and a minimum, there's a point in between them that's going to cause the function to go from being concave up to concave down. That point is your inflection point. And where does that happen? Well, that happens right here on the extrema, okay? If there's extrema on your derivative, then that means there's an inflection point on your original function at that particular extrema on your first derivative. So I'm going to draw this with a different color, okay? I should have a minimum at -2. I should have a maximum at +4. And at that point, between them, I should change from being one direction to the other direction when it comes to concavity. So again, I'm below the x-axis from -infinity to -2. So again, that means I should be decreasing on my original function. Until -2. Then I should be increasing from -2 to 4 because that's where it's positive. And then somewhere in between, I should change from being concave down, as we can see, because that's how we get the minimum, to being concave up, but still increasing. After 4, I should be negative. I should be decreasing because my first derivative is negative. So then here we have our original function with extrema at -2 and +4, and a point of inflection at that extrema on my first derivative. So I'm hoping this made sense. I'm hoping after doing a few more examples, it become easier for you guys. Just make sure that you do your homework and bring your questions to our next class.